Welcome. The title of today's notes worksheet is Ellipses Day 3. This represents for us the culminating piece on ellipses before kind of diving into the next conic section. So why don't we just kind of round it out with some good algebra and maybe an application or two along the way. So why don't we go ahead and dive right in. A couple examples to look at initially here. So this one should just take a couple seconds. Let's see. True or false? It is easier to distinguish the graph of an ellipse from the graph of a circle if the eccentricity of the ellipse is large, which would be close to 1. If you remember, the interval for the eccentricity of an ellipse is between 0 and 1, non-inclusive there. So what do you think? True or false? And the answer, true. All right, good. Yeah, so in this particular case, remember what we saw yesterday is the farther away that the foci are from the center, which would make the eccentricity closer to 1, the more elongated the ellipse, and so obviously easier to distinguish from that in a circle. All right, so true. Good. Now let's go ahead and utilize that. We did something similar to this yesterday, but let's do one a little harder. So it says write an equation for an ellipse. Center is at 2, -4. Vertex at 2, 8, and an eccentricity of 2/3. Okay. Well, I like this one, and I'm just kind of thinking about, we're going to write the equation, so I'm just going to get that set up off to the side there, and then let's see what kind of work we need to do. Again, I would encourage to be visual, so I'm going to go ahead and do that here. You don't have to be that detailed, but if you want to, if you need to, then certainly. So I'm getting 2, -4 is the center. I'm going to go ahead and put that here for everybody. And then 2, 8 is a vertex. So let's be clear on that. So same, we're just going to be going up here to 8. So 1, 2, 3, 4, 5, 6, 7, and 8. And so all the way up here is a vertex, something like that. And that's all I have except for that eccentricity, which remember is a ratio of C to A. Okay. Well, let's see what we have going. First of all, center is 2 and -4, so that's given. I'm going to put a little h and k underneath that. If you want to, great. If you don't need to, so be it. But we will, of course, need the center, so for the top, and I have it, so that's good. Let's go ahead and put our A, B, and C in, and let's see what we have. So A and B and C. We've seen it before. We'll see it again. It all really comes down to those 3 quantities. And I would argue just definitively we have one of those 3 at this point. And here is my center. Here is a vertex. It's a long way up, but I'm seeing A is going to be 12. So I'm going to go ahead and actually kind of write this in. That's your A. Ew, that looks like a 9, so let's do a little better. Oh, and I butchered that, but whatever. All right, A is 12. I hope everyone sees that. So from center to that vertex, as poorly as I drew that in there, you still hopefully see that A is 12. Wonderful. All right, now I think there's nothing at all in this problem that talks about a covertex. There's no information about B. So that we're going to have to put on the back burner. But it's time to go get C. So we saw this before. Let's go ahead and utilize it. So the eccentricity is a ratio of C to A. Now, just as I said yesterday, it doesn't mean that C is 2 and A is 3. It just means the ratio is 2 to 3. And so in this case, that 2 to 3 is some C value over 12. That's what I want to deal with right there. So the A value is definitively 12, and you can do a little cross multiplying here, and I hope you kind of see that C is going to be 8. And I'll put it here as well. All right, very nice. So once we have those 2 pieces, then we just get the third. And we've done it before, so let's get this equation going. C squared is A squared minus B squared without question. 2 out of the 3 are in place. 1 is missing. And remember, I don't really care too much about what B is. I'm just writing the equation, so really I do want B squared, which kind of is helpful here, to be honest. Let's see, C squared. 8 squared is 64. A squared, so that's 12 squared. That's 144. And minus the B squared. And again, you can play around with this if you'd like, but I'm going to bring that b squared on over and then maybe bring the 64 on over there. Oh, 144 minus 64. I'm getting an 80 on that. And again, if you want to go further, you can. It's so unnecessary because we want b squared. That's what's going in the equation, not b. B would be the square root of 80, of course. And square root of 80 should be 4 root 5. I'm going to put that there, not that you need it, but I think it's ready. Hey, it would be great if you could pause the video and write the equation and see if you're just really doing okay with this. Well, let's see maybe how you did. I got mine kind of set up here. I just thought, all right, well, A is 12, so I'm thinking of 144 there. The b squared is the 80, so, you know, it doesn't matter the order. I just put it like that. But I do have to be careful here, so the 144, the 12 squared, goes with the stretch, and it looks like we're going vertically stretched. Hope everyone's okay with that. So the y minus k is what's going to go on top. So I'm getting a y minus negative 4 squared, or really just y plus 4 squared. Okay, great. And then as a result, the x minus h with the squared right above that 80. And I think there's your winner. Again, does the order matter in these two fractions there? If you put this one out in front? No, it doesn't. But make sure these two are under the right variables. The 144 is under the y, the 80 is under the x. That's the key. All right, very cool. Good stuff. Let's go get 3. Let's see if we can put this together. So a semi-elliptical archway has a height of 20 feet and a width of 50 feet. Can a truck 14 feet high and 10 feet wide drive under the archway without going into the other lane? All right, kind of cool. Well, what do you say we draw a semi-elliptical archway? That, I think, is our first order of business, something like that. Yeah, not too bad. And, you know, nice and easy, let's put a couple things into the mix here. I saw this is 50 feet in width, and this is 20 feet in height. Something like that to that, right? How does that look? Okay, good. Now, here's the thing. It's great that we've got that labeled, but what we're going to want to do here is actually model it. We're going to actually want to model this algebraically, which means I think we're going to have to go ahead and try to superimpose some type of coordinate plane on top of my little drawing here. And so you have the choice. You can do this however you'd like. But I would argue you would probably want to position your coordinate plane in one particular way. And based on the center, I guess that's the key. Let's keep this equation as simple as possible. And me just expediting this along, I'm thinking that you want to go ahead and throw a coordinate plane with the center of that semi-ellipse right at the origin. I really think for like 99.9% of these, it's probably the way to go. You know, why not just make h and k 0, 0, as that is going to be an integral part of our equation. So I hope everyone's okay with that. I've got a little coordinate plane in place, and I think that allows us to do a couple things. Okay. Well, with that said, now that I have this, I'm going to talk A, B, and C, as I always do. I don't know what we have or what we need, and I'm also going to think about the center there, too. So I made the center. I made it 0, 0. That's our h and k. How cool is that? That's great. Now, you talk to me about this one. This would be interesting. What do you have? If we're going to model this ellipse, before we even talk about the trucker going through here, you know, we're going to model the infinite number of points on this semi-ellipse. So model it first, answer the question second. All right, well, let's see. I'm seeing this is going to be our major axis, I'm believing, because this is going to be 50, whereas if I stretch this, this is only going to be 40. So this is our major, horizontal. And are you okay with me saying that A right there is going to be 25? Does that sound all right to you? And as a result, actually, if you kind of look at this in detail right away then from here to the top, that is B. So that kind of worked out nicely. So, wow, as a matter of fact, so A is 25, and B is 20, heck, we don't even need C. We don't care about the position of the foci at this point because we're not, it's not part of the equation. So let's get the equation. This worked out beautifully. Here we go. 25 squared, how does 625 sound? 20 squared, how does 400 sound? All right, now here's the question, of course. Variables, where do they go? And H and K, 0, 0, that's nice. I'm thinking a stretch horizontal here, so that 25 squared is going horizontally. So how about x minus 0 squared, or just x squared? And y minus 0 squared above that, how about just y squared? And I think that's really nice, pretty clean. And you can see the benefit of having the center at 0, 0, right? Rather than introducing more numbers there, we can just have h and k be 0 and 0. Okay, that's a good start. Let's pause for just a second and look at it. That equation models really the infinite number of points on this archway. Now let's go answer the question. So it says, can a truck 14 feet high and 10 feet wide drive under the archway without going into the other lane? So I guess there are probably a couple ways to do this. So if I look at this from one perspective and you have another, and we all end up with the same answer, then that's perfectly fine. I'm just kind of seeing this. So this is sort of the middle line right here. We'll kind of the middle line. And it's going to drive on through, right through here, if you can think three-dimensionally for just a second. Going to go right on through. And we do not want the truck to cross here. So the farthest the truck can go towards the center is right here. And so I guess the argument is, if the truck is 10 feet wide, so I'm going to go 10 feet off the center, that would be the case right there, is what is the height 10 feet from the center? That's how I'm viewing it, at least. So the truck is 10 feet wide, so why don't we see, if it's 10 feet wide right here, what is the height when it is 10 feet wide? If it's below 14, and here it is, if it's below 14, then the truck's going to get issues. If it's above 14, then the truck should be fine. So I guess the question is, what is that y value right there? That's how I'm seeing it. I don't know, maybe you're seeing it a different way, but whatever. I guess the bottom line here is, based on my coordinate plane, the horizontal piece is 10. So the x-coordinate is 10. So what I'm going to do, everybody, is literally just put in 10 for x. And let's see what happens when we do that. Kind of an interesting one. I like it. All right, so given one value, find the other, and then let's draw the conclusion. All right, good algebra here, nothing more. 10 squared is 100. So what do you say we solve for y? First order of business, guys, let's bring that on over. So I'm going to get y squared over 400 equals 1 minus 100 over 625. Hope you're okay with that piece. And then I'm kind of thinking about this. This we're going to get from the calculator momentarily, by the way. And then how do you think we're going to solve for y here? Are you comfortable multiplying by 400 and then maybe undoing that square up above? So I'm going to take this in a couple steps for you just so you see. Might run out of room and go elsewhere, but whatever. Let's see what this is. Let's get a decimal on that. What the heck? So I'm going to bring my calculator up here and just get 1 minus, what was that, 100 over 625. And I get 0.84. Nice. Okay. So this is 0.84. Then what do you say? I'm going to come over here, by the way. Let's multiply by 400. So hope everyone's all right with that. Bring that 400 on up. So 0.84 times 400. There we go, 336. Outstanding. We're going to undo the square right there. Officially, we're going to do a plus or minus. That's kind of cool. Talk about that piece in just a sec, but let's go ahead and get that number. So square root of that answer, 336, and we get about 18.33. All right, so we've got plus or minus, really officially, 18.33 feet. Remember, our equation was for the full ellipse. So what's kind of cool about this, not that you have to worry about this at all, is when we're 10 units over, we are 18.3 units above that major axis right there. But also, if you kind of think about that going below ground, kind of like this, the y value down here would be negative 18.33. So, you know, mathematically, obviously, it gives us for the entire ellipse. Not that it mattered here. Really, the idea was 18.33 feet. So if you want to go ahead and get rid of that plus or minus there, that's the key. So long story short, is the truck going to be able to fit under there? If 10 feet across, it is 18.33 feet high? You bet. Truck's only 14 feet high. Oh, very, very cool. Good problem. So take a look at that. We modeled the infinite number of points, and then what we did is we kind of figured out one point on there and drew a conclusion from that. Nice. All right, let's go get into the astronomy piece. So a lot of the applications dealing with ellipses would end up in astronomy. We'll do maybe one or two here together. You'll do some independently. You'll maybe do some with a partner. You know, there's some interesting things we can do with this. So let me just read what I have right here, and then you can look at my rudimentary drawing. Let's see, so elliptical applications in astronomy. Kepler was the one in the 15 and 1600s. Was the first to come up with the revolutionary idea that planetary orbits were not circular, but elliptical. And looking at the eccentricities of the orbits, it's easy to see why this discovery was so controversial. So you can kind of see, remember we talked about the eccentricities as C over A. The closer to 0, the more circular the shape of the ellipse. And you can see, look at all these. I mean, maybe excluding the Mercury one, look how close to 0 most of these are. So very, very round, but not perfectly round. And so just one thing to note here, again, just quickly pasted this drawing in. Here's sort of the planetary orbit. And just one misperception on this is that the sun is not the center of the elliptical orbit. The sun actually is at a focus. So I'm just going to write the word focus right there. So the sun is at one focus, and then obviously another point in space would be the other focus. So as the planet makes its elliptical orbit around the sun again is not the center, but it is at a focus. So again, you'll have an opportunity to look at a couple of those examples on your own and with a partner. We're going to do one with the moon, which actually also happens to be elliptical in nature around Earth. So here we go. Let's do the last one here. Good one to just focus on. I tried to paste in a drawing to help us out with it. So it says, the moon travels about Earth in an elliptical orbit with Earth not at the center, but at one focus. As shown in the figure, the major and minor axes have lengths of, and so this one's in kilometers, but you see here's the major axis. And by the way, just right away, everybody, without even thinking, let's go ahead and throw a 2A under that. Good idea. Major, 2A. Minor, can't forget about it. Minor, 2B. Wonderful. And so what we're going to do is talk about the greatest distance from the Earth to the moon and the smallest distance from the Earth to the moon. So let's do A and B, which kind of go hand in hand here, and I'll just read them and we'll look at the figure and see if we can figure it out. So letter A, how can we find the greatest distance for the moon and the Earth? It's what's called the apogee. That name actually changes when you're talking about planetary orbits, but for the moon and Earth, it's what's called the apogee. So the greatest distance from the Earth's center to the moon's center. What is the apogee? And there's a little hint. It occurs when the moon is at the right vertex in the figure. All right, well, let's go get this figure right here. So first and foremost, everyone, looks like we have, and oh, nice labeled diagram here. Here's the major axis, everybody. See that? Here's the minor axis. Hope you see that. And what we have is the apogee. Here's the Earth, of course, and here's the moon orbiting around. Again, the Earth is close to the center, but it's a little off the center here. Hence, you can see it's a fairly round orbit, but elliptical in nature. And it looks like the apogee occurs right when the moon is here. So put that in place if you would. When the moon hits this spot in its orbit, it is the farthest away from Earth. And so the question, of course, is how am I going to figure that out? Well, I'll give you a hint. and then let's see if you can kind of figure it out on your own before I give a description. Think about A's or B's or C's and tell me how to get from here to here using either A or B or C. So from here to here. And by the way, the center, of course, is right there, give or take. So what do you think? Well, as I look at this distance, I'm going to go from the moon if that's all right with you. It looks like sort of coming from here to the Earth, it looks like this distance right here is A, right? From vertex to center. So all of this distance is A. And then from here to here, center to the focus, is C. So what I'm seeing is taking A and adding C. And that's it. I think that's our apogee. And that's what you're going to find with all the planetary orbits too, is that the greatest distance, very simply, is A plus C. Nice. Well, let's go ahead and find that out then, huh? We're going to need a little help with the calculator, I believe. But let's see what we can get going here. So, first order of business is to get A and B and C. So let me see what we have going. I'm going to get A. So the major axis, which was 2A, was 768,806. Let's take that and divide by 2. And we get that right there, 384,403. So just kind of looking at this, A is 384,403. B, I think, comes next, everybody. So let's go ahead and get B. And B is going to be half of that minor axis, which was given in the problem. That was very nice. So let's see, I got a 767,746. Let's take that and divide it by 2. And there we go, 383,873. So 383 and 873. Nice. Hey everyone, can I use A and B in order to get C? Should be able to. We've been doing it now so many times. That's what makes all this math really connect very well. But let's go ahead and play it out here, guys. So C squared is equal to 384,403 squared minus 383,873 squared. Yikes. And what do you say we just let the calculator do the work and get that C value, and then I'll put it right in there, and then I think we're ready. So, good. I think most of the work is going into this piece. I think it should flow beautifully after we get it. Let's let the calculator do it. 384,403, square it, minus 383, right? So 383,873, and square it. Now don't forget, everyone, it looks like an extremely large number, but that is C squared. So let's go ahead and take the square root of it. So square root of our answer, and we get that. All right, nice. So 2178, and I'm getting about 0.86, somewhere in there. So 2178.8, let me be a little more specific with it. I missed a decimal or two. 85725, that's what it came up with. 85, let me get that right. So 85725. Nice. And so that's our C value. I guess I'll put it in two different places here. Oh my goodness. Let's put that in better. Having issues writing. Calculating looks great though. That's all that matters. So 2178. And now I think I will round because I'm getting a little lazy there. Okay, that looks good. Hey, can we add the A and C? Let's do that. A plus C. From the picture, that is the most logical piece to get the greatest distance. So A plus C, and I'm going to bring the calculator up one time, and let's get that. So I have, and you're doing it with me, I'm sure, 403, add that 2178.86, and that's looking good. So how many kilometers away is the moon at its farthest spot? 404,581.86 kilometers. Wow, that is so cool. There you go. All right. If we can formulate a strategy for B, I think it's going to be quick. How can we find the smallest distance, what is called the perigee? So for the moon, again, we have apogee and perigee. For the planets, they're called by different names, and you'll see those. But how can we find the smallest distance from Earth's center to the moon's center? And what is it? And it occurs when the moon is at the left vertex in the figure. Beautiful. Let's go to that figure. So everyone, if you would, draw the moon right here. So as it works its way around, when it hits that spot right there in the figure, that is the smallest distance. For the moon, it's what's called the perigee. And the question is, how am I going to get it? So let's see. Think about it for a moment and then see if the description suffices. How am I going to get from here to here? Interesting. I think we're going to have to modify this one a little. I'm seeing if I kind of go all the way to the center, right? So from here, which is at a vertex, if I go all the way to there, that's A, right? So if I go just past the Earth to the center, that's A. And then if I take away this little distance right in here, which is C, by the way, then I should be what's left right in here. So let me rephrase. So from here to here is what we're trying to find. If I take A and take away the little c right here, it should give me what we're looking for. And so whereas the apogee was A plus C, the perigee, guys, is A minus C. And again, we did all the work on the first one, so this is going to ride nice and easy here. So let's go A minus C. I'll bring the calculator up for you. You're doing it as well. Let's type 384,403, taking away that C value, 2178.86. And there's our smallest distance. So when the moon hits that spot, it is only 364,224.14 kilometers away. Really, really cool. Last piece. You looked at some of the eccentricities of the planetary orbits. How about the eccentricity of the moon's orbit? Kind of nice. And again, you look at the figure, and sorry, I'll do the calculation in just a sec. You know, obviously this is not necessarily to scale, but if you look at the A's and B's, you know, from the major and minor axis there, they're pretty close together, meaning this is pretty circular. And look how close in the figure the Earth is to the center of the orbit. So I'm picturing a number fairly close to 0. Let's see what happens. Nice and easy, guys. We did all the work. C over A. So I have 20,178, what was that, 0.86 over this big guy right here, 384,403. And that's going to give us our answer. I'll type one last time just for your benefit, and let's get it going. 2178.86. Divide 384, I think it was, 403. And there's your eccentricity, about 0.052-ish, give or take. Pretty circular. Nice. All right. Cool. Good problem. Nice application dealing with ellipses. And what I love about it is it's all math that we're able to deal with. You know, writing equations, working with A's, B's, and C's, talking about the measurement of eccentricity. All good info, all good stuff. All right, why don't we wrap it up there? As I said, you'll look at some applications yourselves on these, and you'll let me know if you have some questions along the way. But this looks great. Some good stuff. And then we'll hit the next conics section coming up. Thanks for listening, of course. Don't hesitate to ask questions. Always, always, always.